Whenever I say the derivative, we're talking about the rate of change of y with respect to x. Whenever I write dy, the d stands for little change in. So dy means a little change in y, and dx means a little change in x. And all together, dy over dx is a ratio. It's a ratio of the little change in y to the little change in x. Another way to say this, with different words, but it means the same thing, is you could say the words, the derivative is the rate of change of y with respect to x. But it's just talking about a ratio of little changes. The second derivative, then, is what happens if I want to know what's the rate of change of dy dx with respect to x. Well, in other words, what's the rate of change of the rate of change of y with respect to x? Does that make sense? Another way I can write the second derivative is if I have some original function f of x. The first derivative would be f prime of x, and then the second derivative would be f double prime. You just write two apostrophes in there to say that we're talking about taking the second derivative of that function. Another way you might see this is if I've got, let's say the function y, and I want to take the, let me fix this. And I want to take the derivative with respect to x of y. It might look like that. But what if I want to take the derivative of the derivative of y? It could look like that. And then lastly, if we want to use the dy dx notation, you're going to see this a lot too. I hope I wrote clearly enough for you to see in the back row. Is this legible? Can you read it, Ian? Okay, good. And for the second derivative, this is again just notation. You just have to be familiar with what it means if you see this. But this is telling you take the second derivative of y with respect to x. But we outright the d squared y over dx squared in the shorthand Leibniz notation. So remember, this notation was named after the mathematician Leibniz. This notation over here was named after the mathematician Lagrange. So if we say Lagrange notation, we're talking about the f primes. If we say Leibniz notation, we're talking about the ratios of the d's. But it means the same thing, and I just need you to know that it means the same thing.
So what would be squared in the, like, d squared y over dx squared? So like, what's the d? Like what? I know that's the little change. So the little change would be squared?
Yeah. Well, so it's like this. Do you see it in orange? I think the motivation here, if you're really curious about why we write it that way, is like you're looking at this, and this is not multiplication, right? Everybody agrees we are not multiplying two derivatives together. This is taking one derivative and then taking another derivative, taking two derivatives in series. It's not multiplication, but naively, it looks like you're multiplying, right? Like, is that a dumb thing to say? Like, it almost looks like you're multiplying two d's together. Even though you're not, it still looks like that. And then in the bottom, in the denominator, this would be like dx squared. Okay. Again, if you're pretending that you're going to multiply. And again, if you're pretending that you're going to multiply, you'd put the y in the numerator, and you'd end up with something like this. And then the other kind of dumb convention for this type of notation, for just the way we've all decided to write this, is we don't write little parentheses around the dx. We just write it like that, you know? And so that's kind of how you get to the point where we have something like d squared y over dx squared. You can't think too hard about it, right? The only thing you need to know is that means take the second derivative. It doesn't make sense. It's just how it is. It's like, to me, let me show you. In the world of what we call dynamics, if we want to talk about dynamics, it's a math field of study. If I were to write this with the little 2 in front of the f, this means f of x. It's like composing the function f with itself. But again, you've seen something similar to this. Sine squared of x does not mean the sine of x, does it? What this really means is you take the sine of x and then you square the whole thing. And so this is an example of like bad notation, or you could even call it incompatible notation. Like, context matters, right? If I know I'm working in the context of like I'm reading a textbook in dynamics, or I'm reading a research paper in dynamics, then that tells my brain, okay, the little 2 means I'm doing repeated function composition. But if I'm reading a textbook about trigonometry, then the sine 2 doesn't mean compose the sine functions, it means square it, right? So context matters. And the same thing here is like, the x squared does not mean I'm talking about a change in x squared. It means I'm taking the second derivative, right? Context matters. And so, yeah, I wish we could be perfectly consistent with notation, but I'm just teaching you the same notation that everybody else in the world uses, for better or for worse. So, it says, find the first and second derivatives of each of the following functions. And to take the second derivative, you have to start by taking the first derivative. So what is the derivative of 5? 0. Cool. And then what's the derivative of 0? It's 0. Yeah. Cool. So then we would say the second derivative of 5 is 0. Let's move on to the next one then. What is the derivative of 7x? 7. Now, what is the derivative of 7? 0. So I'd say the second derivative of 7x is 0. All right. What is the derivative of 3x squared? Very good. That would be 6x. Now, what's the derivative of 6x? 6. So then I would say the second derivative of 3x squared is 6. We good so far? Okay. So this is my original function, x cubed minus 3x squared minus 7x plus 5. The derivative is going to be what? Perfect. So derivative additivity tells us I can take the derivative of each one of those terms separately because I'm just adding them together. And subtracting is the same thing as adding a negative, so again, it's fine. Take the derivative of each term separately, and then x cubed becomes 3x squared. The other terms we've already done today. And of course, the derivative of 5 is 0, so I don't have to write plus 0 at the end. That's the derivative. Now, what is my g double prime of x?
6x minus 6.
Perfect. So, again, take the derivatives of each term separately. 7 goes to 0. You're good. Questions? Nope. Okay. What about this one? My original function is e raised to the power 3x. It was just spam. Silence my phone. Okay, so what's the derivative of e to the 3x?
E to the 3x.
What did you say? Did you say something? No, who said was it AJ? Did you say it? There was somebody besides Gabe talking, and I don't remember who it was. I wasn't looking up at the time, so. So,
Is it e3x squared?
Nope.
Is it e to the 3x plus x? Oh.
So e to the x has the derivative of e to the x, right? But the 3 in there tells me I need to use what rule? What did we talk about last time? The chain rule. So I take the derivative of the outside function, which is like this e to the x function, and that's good. But then I multiply times the derivative of 3x. So I have to multiply by 3. Very good. Yeah, that's a chain rule application. In fact, it's been a week, and it seems like everybody forgot the chain rule, so I'll go ahead and write down what the chain rule is. The chain rule says if I want to take the derivative of a composition of functions, like f of g of x, then that's the same thing as writing f prime of g of x times g prime of x. And in our case right here, the outside function is e to the x. The inside function is 3x. And that way, when I compose f of g of x, I get the composition e to the 3x. Now, f prime is e to the x. G prime is 3. And so whenever I take the derivative of all of this, it's g prime times f prime of g. So that was a quick recap of last week. Now let's take the second derivative. So what's the derivative of 3 times e to the 3x? Nope.
9 times e to the 3x?
Perfect. This is going to be 9 times e to the 3x. Because, and I'll work it out step by step, derivative homogeneity tells me that that 3 constant just goes along for the ride. We don't touch the constant multiples. So this 3 comes from right there. And then the other 3 comes from taking the derivative of e to the 3x. And you've already taken the derivative of e to the 3x. That's 3e to the 3x. And so all of this is that derivative. And of course, 3 times 3 is 9. So I write 9 times e to the 3x. is the second derivative. Honestly, I think for whatever reason, it seems like the chain rule is the part that students struggle the most with. So if you're really trying to prep to get a good grade on your test next week, I would go over the chain rule homework and spend more time with that than anything. I don't know why. It's really hard in retrospect, if it's been like 15 years since you learned something, to remember, like, what was it that was so tricky about the chain rule? I don't know, but something about the chain rule is more difficult than the other things that we learn in this class. So be extra careful with those questions. Okay, my original function is square root of x. And before I take the derivative, I like to remember, what's another way I can write square root of x that helps in calculus? X to the 1/2 power, yeah. Because that allows us to use the derivative power rule. And the derivative power rule says that the derivative of x to the 1/2 power would be what? Very good. Half x raised to the negative 1/2 power. And then when I take the second derivative, it's going to be what? You said negative 1/4 times x raised to what power? Negative what?
Negative 1.
Oh, no. Sorry. I couldn't hear you. I wasn't teasing you, but I just couldn't hear you. Negative 3/2. Yeah. Every time the power of x goes down by 1. So it goes from 1/2 to negative 1/2 to negative 3/2. And I take the second derivative. Okay. The next one has f of x equals x times cosine of x. So there's a special rule we're going to use. What's the name of my derivative rule I'm going to refer to? It's called the product rule. Yeah, product rule. So if I'm taking the derivative of a product of two functions, this is f prime g plus fg prime. And in this case, my f function is going to be, I mean, I know that the whole function is named f. This is just what I do in my head, right? Ignore the overall function being named f for a minute. And in the case of the product rule, what this f means is that you take the first factor, and then the g would be the second factor. And so I'm taking the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. What's that derivative going to be?
Derivative of the first one
Uh-huh.
is 0.
What's the derivative of x?
1.
1. Yeah. The derivative of x is 1. Yeah, if we ever say that the derivative of a function is a constant 0, that means that function has to be a constant number, right? Because think of derivative as the slope of a curve, and the only curves that have perfectly flat, horizontal, 0 slopes everywhere are horizontal lines. And so it has to be a constant. If you take the derivative and get 0, then it has to be a constant. Okay. But in this case, x, like y equals x, makes a line with a slope of 1 everywhere, and so the derivative of x is 1. Now, what is this derivative that we're trying to find? Over here.
cosine x minus x sine x.
Very good.
It would have been negative sine. Oh, yeah.
Yep. Like that. Yeah, because it would be 1 times cosine of x plus x times negative sine of x whenever you work out the product rule. Okay? What is the second derivative?
Negative sine of x minus cosine x.
Okay. So we're going to have inside here the derivative of x sine of x. And to take the derivative of x sine x, we got to use the product rule.
Yeah.
There we go. And if I want to simplify my answer, I would write negative 2 times sine of x minus x cosine of x. That would be the second derivative.
How did you get the sine of x on that second derivative? Oh, sorry, I'm tripping.
Okay. Yeah, it's because of the f prime g part. Let me see what I have up ahead of my notes, because I don't remember if I'm... Okay, yeah, let me give you a little bit of a spoiler for what might come up later in the semester too, because we're going to talk about applications of derivatives later in the semester. And one thing you might be wondering about at this point is like, why do we care about second derivatives? And I'm not going to like spoil this too much. I'm going to keep this short today. But for one thing, I might have a function that describes my position as a function of time. So I'm using p as the name of my function. I'm using lowercase t as my independent variable because t is representing time. If I were to take the derivative of p with respect to time, and I get p prime of t, this is talking about the rate of change of my position with respect to time. It's talking about the ratio of a small change in my position divided by a small change in time. Do you know what that's called? Velocity. This function now gives me my velocity or my speed as a function of time. So if I've got some kind of function or some kind of data that's going to tell me about the position of an object, doesn't matter what it is, it could be a subatomic particle, or it could be a train, or it could be a rocket ship, or it could be an airplane, or it could be a car, or it could be whatever. If I know the position as a function of time, I can take the derivative of that function and it will tell me the velocity as a function of time. It will tell me how fast is the train moving, is the car moving, is the airplane moving, whatever. And then if I take the derivative with respect to time of this velocity function this would now be the second derivative of position with respect to time. And so that's talking about, a change in the change in position with respect to time, So maybe we rewrite it like this in the Leibniz notation if you want to. But this is also then the derivative of velocity with respect to time. And that would be what? How does velocity change with time? Acceleration. This is going to tell me about my acceleration as a function of time. And lastly, you probably remember from your physics class that force is equal to mass times acceleration, right? So one of the things you might want to do at some point in your life as a train engineer or car engineer or aircraft engineer or rocket engineer or whatever is you might want to know, if I apply some kind of force with my engine or rocket fuel or whatever, and I know what the mass of my object is, I know what the mass of the car is, the mass of the airplane, the mass of the subatomic particle, then what acceleration is it going to experience, right? And if I know what the acceleration is, then it's also going to give me information about the velocity and position. I mentioned this earlier in the semester too, we're going to do antiderivatives later. So we'll be able to figure out, given an acceleration function, what is the velocity function, and given a velocity function, what's the position function. So you can actually predict, is your spaceship going to make it to space or not, And how quickly is your train going to reach the next station and things like that. But this is just one example. Second derivatives are actually everywhere. Again, a lot of my examples are going to be from physics, but this is the last thing I'll tell you before we are done, and then we'll move on to doing more examples of derivatives. But and that doesn't make any sense right now. What I was going to say is derivatives show up a lot in physics, and I was hoping for something that was a little bit more readable. So I'll just go up to the top. That little upside down triangle is a way of taking derivatives in three-dimensional space. But it's a derivative, okay? I just want you to know derivatives do show up in physics. The notation looks different from what we're using today, but in Calculus 3, you'll be able to understand that very well. Just got to take Calculus 1, and then Calculus 2, and then Calculus 3. But I only mention that, a little glimpse into the future because sometimes you might want to know, is there any point to taking second derivatives? And the answer is yeah. A lot of good reasons to take second derivatives in science and so on. STEM. Calculus does not go away. One of the great myths I think about math is that a lot of people think that the math you learn at first is going to be the most useful math. And in a way that's true, right? Like everybody needs to know how to add, subtract, multiply, divide, so you can split the bill with your friend when you go to a restaurant, right? But then you pass through this period where it's like, if you don't go any farther, math was a huge waste of your time. I mean by that about college algebra specifically, right? Like if you were going to take college algebra and trigonometry and then stop, and that was your last math class, then why would you need to know about factoring polynomials? You never see polynomials in real life, do you? Why would you need to know about trigonometric identities? You never see those in real life. They don't apply to business. It's just it's goofy. But the more math classes you take after that point, the more and more and more useful the math gets. We're going to do a bunch of real life applications in this Calculus 1 class, but they're going to feel a little bit contrived. We're going to do problems where you throw a baseball in the air and you want to know at what point does it reach the highest point, right? The apogee of your baseball. And it's yeah, that's a real life application, but it's also a little bit silly, right? Who really cares? And so we're getting closer to being applicable with our math skills. But the more math classes you take, the more accurately you're able to describe real things that pop up in the real world that matter to you. And so you should look forward to that. You should think math is going to get more applicable. It's going to get more useful in real life as we go on, and not less useful. Okay, that's the end of my tangent. We're back to taking derivatives. Here's a function, sine of x divided by x. What is the derivative of this function? It's the cosine of x minus, let me think about this for a minute. Because it's the quotient rule, which tells me if I want the derivative of a quotient, it's going to be f prime g minus f g prime. And again, I'm not talking about g because the overall function is named g. When I say g here, I mean the denominator. And so f prime is the derivative of sine good. G is x, so the derivative is, sorry, I don't take the derivative though, do I? I'll leave that alone. Minus f, which is my numerator, sine, times the derivative of x. And the derivative of x is 1. I don't have to write times 1, so I'm not going to do it. And then I divide by x squared.
Where'd that x come in front of the cosine?
Is it just the x on the denominator you just moved it in front of it?
Yeah. This x in the denominator is that g in my derivative quotient rule. And so it stays. Now we get to take the second derivative. Now the second derivative might get a little bit messy, and so what I'm going to do is I'm going to choose a different color of pen, and I'm going to work out this problem on the side here. Let's say that my numerator is x cosine x minus sine x, and the denominator is, and I can just write f and g, I don't have to be really fancy with this. My denominator is x squared. So then, when I need f prime from the derivative quotient rule, I have to take the derivative of x cosine x using the product rule. And so that is going to be cosine of x, because it's f prime g plus f g prime, so minus x sine x. And then that's not all. I don't just have to take that derivative product rule, but I also have to take the derivative of negative sine, so that's going to be negative cosine. And so the good news is that a positive cosine with a negative cosine is going to cancel out, right? So I don't actually have to worry about that cosine or that cosine because they cancel. So f prime is just going to be negative x sine of x. Now let's talk about g prime. What is g prime? 2x. Now I'm ready to write my second derivative using this derivative quotient rule, which says f prime g, which is negative x sine of x for f prime, times g, which is x squared, minus f, which is x cosine of x minus sine of x, times g prime, which is 2x, all divided by g squared, which is x squared squared. And let's simplify this a little bit and make it look nice. Because in the first term, I've got negative x cubed sine of x. And in the second term, I'm going to distribute this minus sign, and I'm going to distribute the 2x so that I get minus 2x squared cosine of x. And then two minus signs make a positive, so it'll be plus 2x sine of x divided by x to the 4th power. And you can probably tell there's even more simplifying we can do. And maybe the only thing I really want to do anymore is just cancel out one x from the top and bottom. And so it's like minus x squared sine of x minus 2x cosine of x plus 2 sine of x. And since I factored an x out of the numerator, I can cancel out one of the x's in the denominator. And so that is a tough problem, isn't it? There's lots of stuff going on there with the quotient rule. And then while we were doing the quotient rule, we had to apply the product rule. Because part of taking this quotient rule was taking the derivative of x cosine of x. And so we had to use the product rule inside the quotient rule. So my only advice is be careful, take everything slow, write really neatly. You know, there is definitely a correlation between students who have great handwriting and students who perform well on tests. Because I've seen so many examples of students who are pretty good at taking derivatives, but on a test question, their handwriting is so bad they can't read what they wrote previously. And if you don't have really neat handwriting and keep your work organized, then it can be hard to understand what you had written previously, and then you make a little mistake because you misinterpreted something you wrote. And with these multi-step problems, it's especially important. While we're talking about it, can everybody read everything I wrote? It's legible? Okay. That was always my biggest complaint. When I took differential equations at Texas Tech, my professor was this Russian guy who wrote on a chalkboard, and his handwriting was so bad you couldn't read what he was writing. And his accent was so thick that you couldn't understand what he was saying. So it was like, I mean, I understood very little from lecture, but I want to make sure at least you can see what I'm writing here. And like I said, checking your answer is always a great idea. Let's do a little bit of a check here. Oh, I don't want to sign up. I want to open calculator. Then we start off with sine of x divided by x. I'm going to name g. G prime of x would look like that, and g double prime of x looks like that. Okay? To check my answer now, I need to type in what did I get for the first derivative, x cosine x minus sine of x over x squared. And double check, does the blue curve look exactly like the black curve? Yes, perfect. So we got the first derivative right. Now let's plug in what I got for my second derivative, which is negative x squared sine x. Minus 2x cosine x plus 2 sine x over x cubed. And now we need to make sure that this black curve perfectly matches the purple curve, which should be my second derivative. And it does. Cool, so that's how you check your answer. That's how you know that we got the right second derivative. And by the way, you know, we were talking earlier in the semester about The derivative tells us about the slope of the curve. So the places where this red curve is increasing from left to right, we should see the blue curve just be a positive number, right? Positive derivative means increasing slope. Where the red curve is decreasing from left to right, we should see the blue curve be a negative number, which it is. And then lastly, whenever I see the red curve be totally flat, like right here at x equals 0, we should see the blue curve be equal to 0. That makes sense. And the second derivative is the derivative of the derivative, and so we should see the same kind of thing happening here, where anytime I see the blue curve increasing from left to right, the purple curve is positive. Anytime the blue curve is decreasing from left to right, the purple curve is negative, and where the blue curve is totally flat, we've got a 0 in the purple curve. So derivative of the derivative. It has the same kind of geometric relationship. Now, I'm going to skip maybe a few of these so that we can have more important discussions, because I know we're limited on time. We got 25 minutes left. This question says find the first, second, third, and fourth derivatives of each of the following functions. So this function is sine of x. What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. What's the derivative of negative sine? Negative cosine. And then what's the derivative of negative cosine? Sine. So it's not asking us for the fifth derivative, but what would the fifth derivative be? Cosine. And what would the sixth derivative be? Negative sine. What would be the seventh derivative? Negative cosine. What's the eighth derivative? Sine. Okay. So it goes in a pattern. I want you to recognize patterns. And by the way, if I were to write something like this, of course that means the fourth derivative. But another way to write this is like this. So if I write a little number 4 in parentheses, the parentheses tell you this is the derivative that we're about to take. This is the fourth derivative. And that way, if I want to take the 50th derivative, I don't have to line up 50 apostrophes. I just have to write the number 50. It'd be hard to count 50 apostrophes to know which derivative to take. And so that's a shorthand notation. Moving on. If my function that I'm starting off with is cosine, I'm not even going to do this one because I think you guys know how to do that, right? I'll leave that for your homework. You can mull that over. Now let's do this function x cubed. What's the derivative of x cubed? 3x squared. What's the derivative of 3x squared? 6x. What's the derivative of 6x? 6. And then what is the derivative of 6? 0. Yeah. And the derivative of 0 is always 0, right? So this function, x cubed, has 1, 2, 3 non-zero derivatives, and then the fourth derivative is 0, and the fifth derivative is 0, and the sixth derivative is 0, and it's always 0 all the way down. Let's pick out this one, x to the fourth power. What is the derivative of x to the fourth? 4x cubed. What's the derivative of 4x cubed? 12x squared. What's the derivative of 12x squared? 24x. And then what's the derivative of 24x? 24. All right, x to the fifth. These are probably I mean, they might be easy enough, but they're also really fast, and so we might as well do these with class 10. What's the second derivative? 20x cubed. What's the third derivative? 60x squared. What's the fourth derivative? What's the fifth derivative? 120. So the fifth derivative of this g function would be 0, right? Because derivative of 24 is 0. Basically, if you've got a whole number power of x, that tells you how many non-zero derivatives it has. If it's x to the fourth power, then the fourth derivative is going to be a constant. If it's x to the fifth power, then the fifth derivative is going to be a constant. Because every time we take a derivative, we take the power down one. And lastly, e to the x. What's the first derivative? E to the x. What's the second derivative? E to the x. What's the third derivative? Okay, great. E to the x all the way down. What if it's e to the negative x, though? What's the derivative of e to the negative x?
Negative e to the x. E to the negative x.
Yep. So this is an application of the derivative chain rule, where I've got to take the derivative of the outside function, which e to the x is e to the x, so that's fine. Then I multiply times the derivative of the inside function, and the derivative of negative x is negative 1. Okay? So then I'd get negative e to the negative x. Now, what's the second derivative here? E to the negative x. Because really what's happening here is you get to keep the negative 1 because of derivative homogeneity. And then the derivative of e to the negative x is negative 1 times e to the negative x, but then the negative 1's cancel each other out. And so you just get e to the negative x in the end. What's the third derivative? Yeah, because it's the derivative of e to the negative x, and we already discussed that one. So it alternates. Every odd derivative is negative e to the negative x. Every even derivative is e to the negative x. Okay? Pattern recognition is the skill that we're working on here. I've got a funny kind of AI story to share, because for a while I was making like a little bit of extra side hustle money doing this gig I found. They were messaging people on LinkedIn who had PhDs in math and trying to get them to sign up to train AIs. What it is it's like Claude by Anthropic is like, they're trying to actually find subject matter experts to like help it work through things. And the problem with AI is that it's really just what's called large language models, which are really just neural networks with transformers. And if you don't know what that means, that's fine. But the idea is that it doesn't actually think logically. It doesn't reason. All it's really doing at the heart of it is like looking through all of the internet data that's been published over the last 30 years, of which there is a ton of data out there on the internet. And then it kind of does a best fit thing, where it takes your question and it tries to fit it to the closest questions that it sees out on the internet, and then synthesizes a response. And that's a good thing. Honestly, that's how a lot of human creativity works too. Like whenever I sit down to write a new pop song, right? What I'm actually doing is not having magic flow from my brain that's just pure creative energy. It's like I'm synthesizing everything I've heard my entire life, I'm thinking about all of the parts of the songs I've liked in the past, and then I put them together in kind of a new way. It's just a new combination of old ideas. That's all human creativity really is. And that's what the AI is doing, is it's looking at problems that are posted on the internet and it's kind of smushing them together in a kind of big data mixer, and then it pulls out an answer that's the closest thing. And that's extremely effective. for most problems. What they wanted us to do in this little job I had is like come up with problems that the AI can't solve, that it gets wrong consistently. The rule was the AI had to get it wrong 4 times in a row. And then if it gets it wrong 4 times in a row, then it was our job to teach the AI how to solve the problem, right? To give it more training data to work with. And the funny thing is if you ask the AI almost any math question, it could always get it right, like almost 4 out of 4 times. Except if you asked it to repeat a process over and over and over again, it would almost always fail. And the reason is because these models are about 90 to maybe 95% reliable. Like if you ask it a math question, it'll get the right answer 90 to 95% of the time. But it'll make mistakes, like 5% of the time, 10% of the time, it'll give you the wrong answer, and you've got to catch it and be a critical thinker when you look at the result. But what you can do then is ask it a question like, what is the 1,000th derivative of e to the negative x? You and I know that every even derivative is going to be e to the negative x, and 1,000 is an even number, so we know that 1,000th derivative is e to the negative x, right? It's pattern recognition. Humans are really good at that. The AI, instead, will try to repeatedly take 1,000 derivatives. And since the AI is only about 95% reliable in making a derivative or any other operation, then after 1,000 times, what's 0.95 raised to the power 1,000? It's almost 0. It's almost guaranteed to fail. And so it'll give you the wrong answer if you ask it to do tasks repeatedly. And so that's how I got a lot of my like stumpers and that kind of job. It was an interesting experience. I'll say that. So anyways, obviously they're working on it. It'll probably improve in the next few months and be able to answer questions like that. But there's things AIs can't do perfectly today. Now, let's talk about this one. It's x times e to the negative x. What's the derivative? E to the x plus what? X e to the x, yeah. This is the derivative product rule in motion here. So I take the derivative of the first factor, 1, times the second factor, e to the x, plus the first factor, x, times the derivative of the second factor, which is still e to the x. What's the second derivative? What's the third derivative?
Could you simplify and just put like 3 plus e to the x plus e to the x plus x e to the x? Oh,
and what's the fourth derivative?
I would have just written it out over.
Okay, so again, this is one of those pattern recognition things. Is you could tell me what the 1,000th derivative is. It's just going to be 1,000 e to the x plus x e to the x. This one is x e to the negative x. What's the derivative? Again, this is a derivative product rule. So f prime, or the derivative of the first factor is 1, then the second factor, and then plus the first factor times the derivative of the second factor. And the derivative of e to the negative x is negative e to the negative x. So that's why I wrote a minus and not a plus. It's a product rule, but the derivative was negative. And what's the derivative of that? What's the derivative of e to the negative x? And what's the derivative of x e to the negative x? We've already taken that derivative. And then let me distribute the minus sign. I get negative 2e to the negative x plus x e to the negative x. Let's take the third derivative. What's the derivative of negative 2e to the negative x? And what's the derivative of x e to the negative x?
E to the negative x minus x e to.
Yep, we've already done that one. So that's 3 e to the negative x minus x e to the negative x. Okay. So we still have the same pattern that we did before, but now there's some like plus or minus things that alternate. Like x e to the negative x is positive in every even derivative. It's negative in every odd derivative. And then we also get this term that's like 1 e to the x, 2 e to the x, 3 e to the x, 4 e to the x, except what's different here in orange in this next problem is that it's e to the negative x, and the plus or minus sign alternates. So that term that has e to the negative x is going to be negative for evens and positive for odds. But that should keep going as you take more and more derivatives. So this is the real test of your pattern recognition skills. And before we do anything else, I want to introduce something called the factorial. The factorial works like this. 5 factorial equals 5 times 4 times 3 times 2. You can also write times 1 if you want, but you don't have to. But 5 factorial is the number 2 times 3 is 6, 6 times 4 is 24, times 5 is 120. So what is 6 factorial? 6 times 5 factorial, right? 6 times 5 times 4 times 3 times 2. And that would be 6 times 120. 720. And 7 factorial, of course, is 7 times 6 times 5 times 4 times 3 times 2, which is also 7 times 6 factorial, and that would be 5,040. This is how factorials work. 4 factorial, of course, then is just 4 times 3 times 2, which is 24. 3 factorial is 3 times 2, that is 6. 2 factorial is 2. 1 factorial is 1, by the way. And then 0 factorial is 1. Sorry, that last one doesn't make any sense, but that's how it is. We define it that way because it's useful. I had this conversation a couple of days ago with my Calculus 3 students. They're asking me like why we made the dot product that way or why we made the cross product that way. It's a Calculus 3 thing. And I just told them, you know, we invent math because it's useful. If you ask why is something that way, the only answer is because somebody found it useful in like an engineering or physics sense. And so we kept it. So if you ask me, why is 0 factorial equal to 1? It's because that's the useful definition of 0 factorial. That's when it makes the most sense. And you'll see why if you take a differential equations class. It's normally the class that you engineers will take your 4th semester in college. You take Cal 1, 2, 3 differential equations. In differential equations, we will talk about why we want 0 factorial to be the number 1. But that's the deal. Now, you understand factorials. Let's talk about the 100th derivative of x to the power 98. What is that derivative? I'll give you a hint. You do not have to take 100 derivatives. Yes. Car just got it. Why is that 0?
Because you can only take 98 before you hit 0, and if you try to find the 100th one, anything after 98 is 0.
Yeah. You've got 98 non-zero derivatives, but then the 99th derivative is going to be 0. That's just how the power rule works. It takes down the power one number at a time. And so based on that, we can say the 100th derivative of x to the 99 power is also 0, right? Because you're doing 99 minus 99 to get you a constant after the 99th derivative. Oh, sorry. Sorry, this is what I meant to write. We're taking the 100th derivative of things right now. But yeah, the 99th derivative would be a constant, and then the 100th derivative would be 0. Okay, what about this one? This one might require a little bit of thought, right? Because if I take the 100th derivative of x to the 100 power, what's that going to be?
1?
It's going to be a constant, but it's not going to be the number 1.
100.
Would you just take 100 times 100 and that'd be your...
It's not 100, and it's not 100 times 100. If you want to start thinking about what it would look like to take the first few, right? I'm going to do this in a different color so you can see. The first derivative would be 100 times x to the power what? 99.
So it was a 100 factorial.
Yeah, there you go. So you might even ask the question like, why do we care about factorials? Right? Why discuss factorials? It doesn't seem useful the way that add, subtract, multiply, divide is useful. Well, here is one useful example of a factorial. Is you could say x to the 100 power. When I take the 100th derivative, the answer is going to be 100 factorial because it's going to be 100 and then 100 times 99. And then the third derivative would be 100 times 99 times 98. And then the fourth would be 100 times 99 times 98 times 97. And by the way, if I was out here taking the fourth derivative, and I get 100 times 99 times 98 times 97, a quick way to write that is to say 100 factorial divided by 96 factorial. Because that might not be so hard to write, but what if I had like this function and I take the 50th derivative, right? So I've got 100 times 99 times 98. Well, then that would be 100 factorial divided by 50 factorial. And that way I don't have to write 100 times 99 times 98 times 97 times 96 and so on.